This next problem focuses on tangent planes and linear approximation. So we're going to be doing both for this function here. So in this we're also going to need some partial derivatives, of course. So the first part, find the tangent plane to f of xy at xy is equal to 1, 1/2. So we want a tangent plane. It looks like z minus z0 is equal to df dx at x0, y0, x minus x0 plus df dy at x0, y0, y minus y0. So let's find each of these components. So first let's find z0. Well, this is f at x0, y0. x0, y0 are 1 and 1/2. This is f at 1, 1/2. And we see for xy, square root of 1 plus sine pi y, we have 1 and 1/2 square root of 1 plus sine pi over 2. And the sine of pi over 2 is just 1. So we have square root of 2 over 2. z0, next we want df dx at 1 and 1/2. So if we look at this, df dx, well, that's just one term, and that's just going to be y square root of 1 plus sine pi y at 1 and 1/2. So that's going to be 1/2 square root of 1 plus, well, sine of pi over 2 again. It's going to be 1 plus 1. That's square root of 2 over 2. df dy at 1 and 1/2. It's going to be a little bit trickier. Our first term is going to be x square root of 1 plus sine pi y. And that's because that's from our first term in the chain rule, right? So that's this one. For the product rule. So next we're also going to have this other term. So we have also plus x y d by dy of 1 plus sine pi y to the 1/2. Oh, and we're going to evaluate all of this at 1 and 1/2 when we're done. This is x square root of 1 plus sine pi y plus xy d by dy. So we're going to do the derivative of the inside first. So we have pi cosine pi y, and then we have the derivative of the square root. It's 1/2 1 plus sine pi y to the minus 1/2, all at the point 1. Oops. 1/2. Ran out of room there. Okay. So let's try this on the next page. We're trying to find df dy at 1 and 1/2. And we just found that to be x square root of 1 plus sine pi y plus 1/2 xy, or pi over 2 xy cosine pi y 1 plus sine 1/2, all at 1 and 1/2. So if we plug this in, our first term is going to be 1 times square root of 2 again, because we have 1 plus sine of pi over 2, and the square root, plus, well, we have pi over 2 times 1/2 times cosine pi over 2 times stuff, but that doesn't matter because cosine of pi over 2 is equal to 0. So all this stuff is 0. So really all we end up getting here in the end is square root 2. Okay, so now to write our tangent plane. Again, we know that we have z minus z0 is df dx at 1 1/2 times x minus x0 plus df dy at 1 and 1/2 y minus y0. So we found that z0, let's go ahead and look at that. z0 is square root of 2 over 2. So z minus square root of 2 over 2. df dx at this point was also square root of 2 over 2. And we have x minus 1. Right, that's x0, that's y0. Plus df dy we just found to be square root of 2. Y minus 1/2. That's y0. Okay. So, you don't have to simplify it. That's your tangent plane, and that's fine. Okay, here's the next part. What does the next part ask? Use this to approximate the number c is equal to 0.54 times square root of 1 plus 0.6 pi. So I'll write this number up here. Okay, so the first thing we're going to notice is that we have this 0.6. We know we're going to need something from the last step. So we have 0.6 here times 0.9, that's 0.54. 1 plus sine of 0.6 pi. So we can notice that this is equal to f at 0.6. Oops, sorry. F at 0.9, that's our x value. So this is our x value. And 0.6, and you see this corresponds to our y value, not the whole thing, just 0.6. Because if you look at our function, that's exactly what our function was we have x times y, 1 plus sine pi y. So immediately when you look at a problem like this, you should say, oh, I have something that looks like my function here. Okay. So what we notice is that this is close to f of 1 and 1/2, right? Because 0.9 is close to 1 and 0.6 is close to 0.5. So we want to use linear approximation. On f of x, y near the point 1, 1/2. So the way we're going to do that is, if you remember our definition for L of xy, well, L of xy is just equal to z in our tangent plane formulation. It's just equal to this z. So what we're going to do is we're going to grab this one and bring it over here, add it on to the end or the beginning, and then just solve for z. That's what the tangent plane is. So z, which is, I'll write this on the next line, square root of 2 over 2 everything had this. Square root of 2, square root of 2 over 2, x minus 1, plus square root of 2, y minus 1/2. Okay, so this is our linear approximation. And what we should find is that L of 0.6, or 0.9 first. L of 0.9 and 0.6 is approximately equal to F at 0.9, 0.6. So what we're going to do is we're going to use L to find this number C, which is equal to C, which is the number which is equal to F of 0.9 to 0.6, and we're going to find it by this linear approximation. So if we just do L of 0.9, 0.6, well, this is square root of 2 over 2 plus square root of 2 over 2, and we have 0.9 minus 1 plus square root of 2, 0.6 minus 0.5. So this is square root of 2 over 2 plus square root of 2 over 2. And 0.9 minus 1 is 0.1, or 1/10, plus square root of 2, 0.6. This is going to be minus 1/10, I'm sorry. 0.6 minus 0.5 is 0.1, which is 1/10. So this is square root of 2, and we have 1/2 minus 1 divided by 20 plus 1 divided by 10, or square root of 2 times 11 over 20, once you work it out. Okay. So now this is a lot easier to find. This is more informative than what we started with, this number for C. If this number had this ugly sign in it, which was hard to approximate. So now we have something which is better. This number is exact. Okay. So there's one more step to this problem. If f of xy measures some quantity, and we make the error in the measurement of x is plus or minus 0.1, the error in the measurement of y is plus or minus 0.2. We want to put bounds on the true value of f of xy. And xy is equal to 1, and that should say 1 and 1/2. Okay. Okay, so errors in the measurement of x means that dx is equal to 0.1 because it's an error of 0.1, and dy is equal to 0.2. It's an error of 0.2. dx is equal to 0.1, dy is equal to 0.2, and we want df, right? Because this is error in df. It's going to be a small error. Well, we know, this is the important part of this, is the rule for differentials. df is d by dx at 1 and 1/2. So this is the point that we want to find the error at. And dx plus df dy at 1 and 1/2 dy. Well, we've already found this stuff. This is square root of 2 over 2. dx is 0.1. This is 1/10. Plus square root of 2 df dy, and this is times 2/10. So I'm going to write this as square root of 2, and we have 1 divided by 20 plus 4 divided by 20. Right? This is square root of 2. 5 divided by 20 is 1 divided by 4. So square root of 2 over 4. That's the error we're getting at. So what we find is that f of 1 and 1/2 is less than or equal to, well, we're going to find the value we did for f of 1 and 1/2, which is, we called z0 plus square root of 2 over 4, and it's greater than or equal to z0 minus square root of 2 over 4. What did we find z0 to be? Well, that was just square root of 2 over 2, if you remember. So we have square root of 2 over 2 minus square root of 2 over 4 is less than or equal to f of 1 and 1/2, which is the rest less than or equal to square root of 2 over 2 plus square root of 2 over 4. So square root of 2, 1/2 minus 1/4 is equal to 1/4. So we have square root of 2 over 4 less than or equal to f of 1 1/2, which is less than or equal to, well, we have 1/2 plus 1/4, which is 3/4, so 3 square root of 2 over 4. So this is the true bound on what f can be if we make errors in the measurement.